Okay, chapter 19, magnetism. First, let's look at the properties of a magnet. The like poles of a magnet repel and the unlike poles attract. This is similar to electric charges, positive charge, negative charge. They are attracted to each other. For a magnet, if I place the magnets with different polarities facing each other, they will attract. Next, magnets have two poles, the north and the south poles. Okay, the magnetic field is the strongest at the poles. Magnets attract magnetic materials such as iron, nickel, cobalt, and steel. Okay, a freely suspended magnet will come to rest in the north-south direction. So this is a magnet. It will point towards the magnetic north. Next, how to identify a magnet? Okay, the only test is for repulsion. Because a magnet can attract a magnetic material, okay, such as nickel. Okay, even if I reverse the direction of the nickel bar, it will still get attracted towards the magnet. But if I were to place another magnet, okay, it will be attracted in this configuration. But if I were to reverse it, it will get repelled. And that's the only way to test whether the object is a magnet or a magnetic material. Next, let's look at what magnetism. Okay, magnets are made of atoms at the subatomic level. Okay, electrons circulate around the nucleus and they spin. So let me give you an example of Earth. So this is Earth. And this is the Sun. As Earth rotates around the Sun, it itself is spinning on its axis. Similarly, an electron orbiting around its nucleus, this is a nucleus, an electron as it orbits around the nucleus, it is also orbiting about its own axis. And this electron, this orbit of the electron gives rise to an electron spin. So this is what the meaning of electron spin. This electron spin gives rise to atomic magnets. So each of these electrons are magnets. Then using the domain wall theory, let's come to the domain wall theory. These are individual magnetic spins. So you can see that all these spins are misaligned. Okay, so this is just a unmagnetized material. So if we can align all the spins in the same direction, it becomes a magnetized material. As you can see, there's these lines here. These are actually different domains. So each of them are its own magnetic domains. The lines in pink is actually called a domain wall, okay, which separates the different magnetic domains. Okay, let's look at magnetic induction. Okay, we can actually make an object that is of magnetic material such as your nickel, your iron, your cobalt, or your steel to become a magnet. Okay, so it's like inducing magnetism. What we can do is that we can have a magnet placed near a iron bar. because of its magnetic field coming out from the magnet, you realize that drawing the magnetic field, it's similar to how we do for electric field. This magnetic field causes the domains or electron spin to point in a certain direction, inducing the magnetism in the magnetic material. So another way to create a magnet is to use a permanent magnet, okay, to stroke a magnetic material. Okay. Another way is also to use electricity. That's what a current carrying solenoid. This is a coil, okay, that we run the current through, and this creates a magnetic field. So how do we determine the magnetic field direction of this coil? We look at the right-hand grid rule. Okay, so let's look at magnetic fields now. Magnetic fields and electric fields are quite similar. So for a solenoid, as we run the current through, we can use the right-hand grid rule, and we can actually see the direction of the magnetic field. Okay, using the right-hand grid rule. Your fingers curl in the same direction as the current flow. Your thumb, okay, will point in the direction of the North Pole. So the back will be the South Pole. Okay, next. You can pause here to look at the work example 1. So we talk about creating magnets. So how do we destroy magnets? It's something called demagnetization. You can either hit the thing using fire, flame, or physically hit the magnet. Another way is the electrical method. That's how we talk about creating a magnet using current, a solenoid. If you reverse the direction, okay, using an alternating current, AC current, okay, you can actually mess up the electron spin in the magnet, and then using the passing AC current, because the current changes direction each time, so you are forcing it to become north-south, north-south-north all the time. So using the coil, so if you keep reversing it between state 1 and state 2, it messes up the electron spin. As a result, the magnet loses its efficiency. Okay, next, let's look at two types of magnets, temporary and permanent. Okay, so temporary, like the word mentions, they retain their magnetism in the presence of electric current or a permanent magnet. So if I put a permanent magnet, the material, like magnetic material, can have its magnetism, can induce the magnetism in it. But if I take it away, it just returns to be a magnetic material, no longer a magnet. Okay, permanent does not require the presence of electric current or a permanent magnetic field. There's two types of magnetic materials, soft and hard. Okay, soft magnetic materials have a stronger induced magnetism, okay, as compared to hard materials. Okay, so some examples of soft magnetic materials are like iron. Hard will be steel. Okay, iron is easy to magnetize and demagnetize, so it's good for placing in solenoids. Okay, because sometimes if I require the magnetism, like in the junkyard, when I'm trying to pick up the magnetic materials, sorting it through the junk, I can put the current in, and then when I remove the current, it ceases to be a magnet. Your permanent magnets are usually steel, okay, because it's hard to magnetize or demagnetize. Okay, so how do you have to be able to describe how you use a compass or bar magnet to determine the direction of a magnetic field. So as you know, electric fields and magnetic fields are invisible to the human eyes. So the way is, if you have a permanent magnet, as you can see the north-south, you place a compass within the magnetic field. Okay, the compass will align itself to the magnetic field. So you repeat the same process. Okay. Repeat the same process. You realize that you are able to plot out the magnetic field. You place a compass here at the south pole, it should point in. And from this, you can connect them and you will form the magnetic field. So you do it the same for the other side. If you were to put one here, you'll point this direction. You'll point this direction. This direction. You can connect them together. And then you will get your magnetic field lines. Okay. So another way is also to sprinkle iron fillings around the magnets. You get a sort of a pattern. Okay, so drawing magnetic fields, same as electric field, it's pointing outwards from the North Pole and inwards for the South Pole. Please take note that magnetic field lines, same as electric field lines, do not cross or intersect with one another. The distance between the magnetic field lines represents the strength of the magnetic field. So it's very close. Like the picture on the left, it's strong. Magnetic field. Okay. But if it's something like this, where the field lines are very far apart and spaced, so it's sort of a weaker field as compared to this. Great. Magnetic field. Okay, next, how we draw for electric field is the same. Imagine a example is a positive charge and a negative charge. Remember that it's outwards from the positive charge and inwards to the negative charge. So you see that they're actually quite similar. An example is this. We have two light poles. You have two positive charge. Same thing, they repel each other. And you will create a neutral point where the X is. Okay, look at more complicated ones. You have two bar magnets placed side by side, whether the poles are facing each other or they're opposite to each other. And that's the end of magnetism.